I'm Lee, this is Jump. I'm going to explain to you the concept of fitting a line to data. Look at this data here, it appears to be linear. I want to draw a line that summarizes these 6 data points. Here's a line that I could try. Looks good. I have 3 points above the line, and I have 3 points below the line. So one could say that I'm sort of hitting at an average. However, this line is not unique, so it might not be the best. For example, I can simply maneuver this line like this. Now I've got 3 points above and 3 points below. Maybe not a great line for describing this process. I can split it like this. 3 points above, 3 points below. Again, not the greatest fit. So maybe our above and below concept isn't what we should use to say this is a great line. Let's try something else. Instead of looking at just counting points, let's look at the distance from each point to the line. These are called residuals. And as you can see, as I adjust this line, the residuals grow and shrink along with it. Over on the right side here, you will see a sort of thermometer that shows you the sum of these residuals. If I add them all up, this one is a positive number, this one is a negative number, slightly positive, negative. If you add those up, you get this sum that I've put into this little thermometer over here. In fact, if you look, we've got our residuals are just above 0. So if I do just a little tiny bit of adjustment, I can probably get those to hit just at 0. In fact, let me use one of Jump's properties here to add a line that's right at 0 so I can tell exactly when I hit it. There, perfect. My residuals cancel each other out. However, that also is not the best criteria because I can change the line drastically and still come up with a line that has its residuals equal to 0. Why does this happen? The math is easy. In fact, there's a line that will cancel all the residuals out. So just the plain residuals aren't a good idea. We could use absolute value, but that's very complicated. The best idea was given to us by this guy, and it uses the squares of the residual. Now, geometrically here, I can draw the squares of the residuals by adding the squares onto each residual's side. So instead of a residual from the point to the line, I've also got a square that has that residual as a side. Again, over here you see my thermometer, which shows the sum of those squares. That is, the area of each one of these squares. If you added it up, you would get this sum over here. So, I adjust the line as I did before, and you can see that the sum of the squares goes up and down as I adjust the line. But here we've got a curious property. As you note, the sum of squares will go down to a certain point and then rise again. This in fact is going to be true all the time. There's going to be a smallest value for this sum of the area of the squares. That, in essence, is what we call the least squares criterion, the line that has the smallest area of squares of any other line. If I turn on the actual least squares line as computed by Jump, here you'll see it in black. Over here on the thermometer, a line has been drawn that shows the squares that are associated with that line. So, in fact, if I just show you the squares for the least squares line, here in green, there's no way I can get anything smaller than that. So I'm going to turn my line and my squares back on and align my line just perfectly with the least squares line. And as you can see, over here, I have exactly 196.6. And if I move my line either above or below, there's no case that I'm going to get any smaller than 196.6. That's the best I can do with this criteria. That's it. That's the least squares criteria. You've got a key to statistics. Once again, I'm Lee. This is Jump. Thanks.